Welcome to the ERIGRID 2.0 Massive Opening Modeling course module number 4 called Multi-Energy Networks Part 3 Example Multi-Lab Experiments. This module consists of 3 parts and this is the third and last one. Specifically, this part will focus on the guiding example developed for testing the laboratory middleware, features, and services present in the first 2 parts of this module. My name is Giuseppe Silano. I'm a tenure researcher at Ricerca sul Sistema Energetico, a public control research organization located in Milan, Italy. In the first module, it has been introduced a need for conducting experiments with the multi-laboratories or to be more technical research infrastructures. Additionally, it has been presented the available tools, the main advantages and known limitations. The second part of this module, instead, it has been focusing on the distributed laboratory middleware, specifically the software architecture developed for making them connecting the lowest level, the SCADA system that directly communicates with the hardware, with the highest level that regards the web services that connect directly the facility, the laboratory with the end user. Additionally, it has been introduced the Universal API along with the services and the configuration management tools that have been designed and developed within the ERIGRID 2.0 project. Here is the outline of the presentation. First, we will focus on the background and motivation, recalling the concept that also have been introduced in the previous part of these modules. Afterward, we will introduce the guiding example. The example has been set up having in mind the key focus of the experimentation, that is to demonstrate and assess the validity and effectiveness of the middleware and the tools designed within the project. It will follow the distributed research infrastructure setup and a discussion of the experimental results. Finally, this presentation will discuss the tool and the services that have been utilized for executing, running the geographically distributed simulations, the lesson learned, and the known limitations. Conclusions and future work will wrap up the discussion and will briefly present what are the next steps of this experimentation. In the evolving landscape of multi-energy systems, the drive towards integrating diverse energy sources and optimizing their operation remain a pressing concern. This integration is crucial as it encompasses various dimensions of energy systems, including power, heat, and transport, all undergoing a significant transformation due to the decentralization, the decarbonization, and the digitalization. Traditionally, research in this domain has been skewed towards optimizing the planning and operational strategy within isolated engineering frameworks, often overlooking the intricate interconnection and interdependencies that exist among the different energy networks. Fortunately, recent advances have triggered a wave of innovation aimed at addressing this complexity with a significant emphasis on development of new tools and methodology that span across different energy domains. Notably, the concept of hardware and geographical hardware in the loop and geographically distributed simulation have emerged as a pivotal in enhancing the validation and deployment of novel multi-energy systems. In the two images reported in the right side of this presentation, we can find a very simple example of geographical distributed simulation. The first one, the one is located on top and here depicted with the red box is synchronous. The other one that is located on the bottom part of this presentation instead is asynchronous, What's the difference? The difference mainly lies in the presence of a trigger signal that makes the sending and receiving with a regular time interval. Mainly with these two circuits that we can imagine to be located into different places that can be geographically distributed. For example, one in Norway, another one in Italy. Voltage and current signals are packed and sent via UDP through internet. This is more or less the same that happens when we visit a website over the web. So here we can present the key contribution of this presentation, mainly summarized in three bullets. And this presentation will explore the intersection and technological advancement and their practical application, particularly emphasizing the use of hardware and loop in geographically distributed simulations in multi-energy systems, specifically within the framework of the H2020 ERIGRID 2.0 project. It will examine the deployment of the software middleware Jadder and the universal API for establishing a secure, reliable, high data rate and low latency communication between the research infrastructures. A motivating case study will focus on providing ancillary services to empower tweet strategies in a local multi-energy district, examining the impact on the electrical and thermal networks. This initiative aims to enhance power system flexibility as requested by the transmission and distribution system operators, utilizing a combination of electric and thermal storage systems alongside the demand response strategies for controllable loads such as heat pumps and electric boilers. Additionally, the heating system is designed to offer flexibility to the electrical system, for example, for the congestion management and power balancing services. This case study considered here explore the provision of critical services to the electrical grid with particular emphasis on congestion management, including the constraint associated with the electrical import and export and regulating power provision. The focal point of this case study is the assessment of a centralized controller within a geographically distributed multi-energy setup. This analysis is crucial for understanding the operational dynamics of the system components interconnected across various regions. The distribution grid is the Secret low voltage distribution benchmark that is depicted in the bottom part of this slide. It is characterized by 0.4 kilovolts and running at 50 Hertz, and the resources are controllable current sources, allowing precise control over active and reactive power through the calculation of the current magnitude and phase relative to the bus voltage. The experimental setup, as we briefly said, encompass various laboratories that are distributed across Europe, and it's mainly divided in a three-party system: an electrical grid with energy sources, a thermal network, an advanced control system, all graphically represented in the figure reported in the right side of this slide. The electrical infrastructure, the blue dashed box, includes the distribution grid, a few controllable units. And the network is simulated through an RTDS real-time simulated located in the Netherlands at Delft facility with two physical different nodes virtually interfaced with the geographically distributed setup. These nodes that mainly are the point of coupling 2 and point of common coupling 4, referring to the previous distribution network, are connected to a battery energy storage system located at Sintef in Norway, and combined it power, CHP, located in Italy. Instead, for what regards the terminal infrastructure, that here is depicted with the red box, it is divided into two subsystems. The first is a district heating network located in Denmark at the Technical University of Denmark, so DTU, interface with the CHP located at RSC that we also mentioned before when we were describing the electrical part of the system. And this is connected also with the net electrical coupling unit, as we can see in this figure. The second subsystem, so the electrical, the thermal part, is interconnected also with the thermal load and electrical heat pump, both located in Greece at Greece. Just to be practical, we are talking about this part. Finally, the control system, here depicted with the green box, deals with accurately determining set points for these controllable entities to ensure that the delivery of required services takes as required services. It takes as input the state of charge of the battery energy storage system, along with the system state and various that are mainly various inputs that comes from the network and provides as output active and reactive power for the various elements of the network. For instance, the active and reactive power for the battery energy storage system, the on-off signal for the heat pump at Greece in Greece, and so on. Before going deep into the experimentation, it is important to recall the tools that allow the different laboratories to be interconnected with each other. The universal APIs specifically provides a simplified and standardized interface to easy deployment, and following a service-based approach at the foundation of this architecture that has been also presented in the second part of this module, we can find the pieces that are directly connected to the hardware. This means Raspberry Pi, FPGA, servers, local virtual machine, whatever is directly connected to the field of our laboratory. Instead, the platform layer, we have the containers, the network emulation, and overlays that enable the communication between infrastructure layers and the software layer. Instead, on top of this, at the software layer, we can find the transporters like Jandar and Villas that we also see in the first part of this module, and other components such as Mosaic, the time synchronizer. Finally, on top, we can find the interface layer, where we can find the web services that are routine, that are in execution, or we can find the common interface that the end user used to directly connect with the hardware, so passing through all the chain, all the level of this architecture. Here is detailed the software framework developed to facilitate the communication among the research infrastructure engaged in the experimental setup of the motivating case study. At the core of this framework, there is the deployment of the universal API powered by the Gender middleware. And the key advantage of the gender meter well is its ability to enable secure and efficient data exchange between the research infrastructure via an HTTPS secure internet communication functionality that mainly includes replicating infrastructure data across network nodes, ensuring that data is captured in a local data, stored in a local database, and simultaneously mirrored in a cloud-based database. And right after send to all the research infrastructure that are involved in the experimentation. This approach guarantees data consistencies, redundancies without altering or altering the data structure. Moreover, this infrastructure also works in a centralized fashion with all the advantages and drawbacks of this configuration. We can see on the left side of this presentation here exactly a schematic that represents how the gender architecture works. Instead, here it's reporting the QR code that directly connects to the open source software that has been made available with all the tools and services developed for the guiding case study presented here. To validate the effectiveness of the proposed experimental setup and demonstrate the feasibility of providing ancillary services through power-to-it strategies in a local multi-energy district, a sector coupling experimental demonstration was conducted. The performed experiments demonstrated the impact of providing flexibility services on both the electrical and thermal network. And the amount of flexibility that was requested by the system operator is achieved to the control of electric and thermal units such as the storage system, the heat pumps, the thermal loads, the electric boilers, and so on. The distributed network is the one that we already saw during this presentation. This is the low voltage network that is also reported in the bottom of this presentation. And in order to make the communication between the research infrastructure, the universal API were used. Given the slow dynamics that mainly is due to the thermal part, the frequency rate was operating between 1 and 2 Hz. Two distinct working scenarios were delineated. The first one that is an overvoltage scenario. This scenario addresses an overvoltage condition triggered by a photovoltaic generation, either located, if we look at the network that is reported in the bottom of this presentation at PV1 and PV3, located at the point of common coupling 4 and 3, respectively. And the condition is coupled with a low electricity demand. It's worth noticing that the thermal part of the experiment does not play any role in this scenario. The second scenario instead is another voltage scenario. In this scenario, we examine an altered voltage condition resulting from reduced or non-existent photovoltaic generation and an elevated electricity demand. It mirrors the overvoltage case with the critical distinction of employing negative threshold values for operational parameters. And this condition necessitated engagement of both the CHP that is located REC in Italy and the DHN that is located in Denmark at the DTU facility. Here we can find the outcomes of the overvoltage scenario. I'm addressing the high PV generation coupled with the low electricity consumption that is leading to an overvoltage condition. To prepare for this experimentation, TTU, where the single voltage benchmark distribution grid. It's located and it's running on RTDS simulator, also generated the PT profiles and the simulated low profiles. And these were used for inducing a significant voltage rise at nodes connected with the RSC and SINTEF. This means with the nodes that are connected to the battery energy storage systems and the CHP. So here, an active power consumption was used to mitigate the voltage deviation, specifically SINTEF, so the battery energy storage system, employed a simplified control approach, adjusting the active power set point of the battery in a stepwise manner. And this means that a significant power consumption was activated if the voltage rise exceeded 5% and deactivated if it dropped below the 0%. This was used for ensuring stability during the test. Similarly, RSC, so this means the CHP, mainly employed the same hysteresis approach, but in this case, for controlling the consumption of the heat pump located in CRES, that it's worth remembering that it's just a on-off signal. And in this case, it's also important to note that the 5% threshold value is just an indicative value that was chosen for the sake of simplicity during the experiment. And also is important to note that they combined heat and power, so the CHP and the distribution heating network located in Denmark didn't play any role, as the scenario does not need to generate any active power in the network, but just balancing the load. In the figures are also visualize are also depict the state of charge of the battery energy system over time, remembering that the battery energy storage system is at the SINTEF lab in Norway, and additionally it's also reported the reactive power profiles of SINTEF and RSC along with the references. Here, I reported instead the results of the undervoltage scenario, where the voltage at the coupling point of SINTEF and RSC suddenly drops below the reference value of 240 volts due to a low or zero PV generation or high consumption in the grid. The procedure is the same as the one that we saw in the previous slide, but in this case, what it happens is that the threshold values change. This means that we have a negative threshold value of minus 5% for activation and 0% for the deactivation of units. So without going too deep into the experiment, what we see is that in order to restore the value of the voltage to the reference value or a value that is close to it, in this case, RSC needs to turn on the CHP. The heat pump at CRES goes to zero in terms of the activation signal, so it's deactivated. And the battery storage system stop charging, as we can see from the signals that are reported in this slide. So, as we know, the active power does not play any role in restoring the voltage value, but instead is the reactive power that allows for the voltage restoring. But in this case, in order to produce the reactive power, some active power has to be also produced, and this is stored in the thermal network at DTU. To conclude, here I reported the service developed within the ERIGRID 2 project that have been used for the guiding case study. Specifically, they are the data exchange, This one guarantees a seamless exchange of data by enabling the interface between the multiple data formats and protocol, and it also allows the control of the data rate between the research infrastructures. The second one is the network monitoring. It addresses the problem of long distances between the research infrastructures that are connected over the network. This might introduce significant latencies, therefore impacting the accuracy and the stability of geographically distributed simulations. In order to address these issues, the well-established Perforce Sonar tool suite was adapted and used for this purpose. And finally, the third service that was used for this experimentation was the time synchronization service. This service allows for aligning the experimental results, specifically using the global positioning systems, the network time protocol, and the precise time protocol. As we said, all these services were used for the experimentation and therefore for the motivating case study. However, it's worth noting that not all the services are perfect, of course. Indeed, although laboratory middleware offer numerous advantages such as ease of deployment, modular architecture, wider support, and etc., they have also some limitations. They can mainly be summarized in data exchange rate and the need for resource infrastructure adapter. For the first one, laboratory middleware comprises multi-modular tool and services, each typically operating at different rates. Consequently, there is a trade-off between ease of use and data exchange rate when attempting to harmonize some of these services. Instead, regarding the second one, this means the need for a research infrastructure adapter, a limitation of the use of the universal API paradigm is the requirement of a last mile laboratory adapter. This means that in order to use middleware, in order to use the universal API, something needs to be done locally in order to interface the SCADA system and therefore the hardware with this high level infrastructure. To conclude, this module demonstrated the feasibility and effectiveness of employing geographically distributed simulations and hardware-in-the-loop technologies to enhance the robustness and the responsiveness of multi-energy systems. And through the deployment of the gender middleware and the universal API, secure and efficient communication was maintained across distributed research infrastructures, facilitating the real-time data exchange and operational costs. Future works include the refinement of the presented technologies and the validation on other multi-energy domain scenarios with the aim of investigating the applicabilities, the performances, the limitations, and impact on the grid management. Thank you for your attention.